Hello, and in part 3 we're going to look at this standard form equation for frequency responses in a bit more detail. This is the standard form of the equation that we've derived. The frequency response is g times j omega to the power of n, where n is the number of roots of the numerator which occur when j omega equals 0, times the ratio of a load of factorized terms of the numerator and the denominator polynomial respectively. And we can characterize this function perfectly well and therefore work out the frequency response at any frequency if we know g, n, the value of all the other zeros, and the value of all of the poles. Now the term g does have a convenient physical meaning, and you can see that if you consider what happens at very, very low frequencies. If you think about all of the terms on the numerator and denominator of the expression on the slide, they all look like this sort of form. 1 plus j omega divided by a constant, which is characteristic of the circuit. At very low frequencies, omega is going to make this term here much, much smaller than 1. So at very low frequencies, we can approximate all of these terms to be approximately equal to 1. And that means that our total expression for the frequency response, h of omega, ends up being g times j omega to the power of n. If n is 0, which means that we don't have any roots of the numerator at 0 Hertz, then we could write h of omega equals just g at low frequencies if n is equal to 0, if there are no zeros at 0 Hertz. If there are zeros at 0 Hertz, then the best we can say is that at low frequencies, these are all for very low frequencies, h of omega is equal to g times j omega to the power of n. Now, what do we mean by very low frequencies? How low does the frequency have to be for this to be accurate? Well, it has to allow us to make this assumption, that for all of the terms on the numerator and the denominator of our full frequency response expression, we have to be able to approximate these brackets to be equal to 1. And that means we have to be able to approximate j omega over minus all of the zeros and all of the poles to be 0. All of these terms have to be negligible. And these terms are going to be negligible when omega is much, much less than Zn. Or I guess I should write much, much less than the modulus of Zn, because most of these Zn's in practice are going to end up being negative. It's true of all the poles as well. If we're going to be able to neglect all of these terms in the denominator, then omega has also got to be much, much less than all of the pole frequencies too. But as long as that's true, then we can make that approximation. And if there are no zeros at 0, then we can identify the parameter g as just being the gain at dc. At this point, it's useful to think about this total frequency response equation in terms of the product of all of these terms individually. And we can see that the total frequency response has a whole set of factors in it. One is this term that we've just derived, the frequency response at very low frequencies. And then there's the effect of all of these terms which we can separate out in this way. This is the effect of this 0, this is the effect of the pole P0, and so on. If I'm concerned about the amplitude response, which in a lot of cases we will be much more concerned with the amplitude response than the phase response, I could write this in the form the modulus of h of omega, because that is the amplitude response, is equal to the modulus of g times the modulus of j omega to the power of n times the modulus of all of these other terms, j omega over minus zn and so on, and 1 over 1 plus j omega over minus p naught and so on. If I then convert this equation to an equation in terms of decibels by taking 20 times the log to the base 10 of both sides, and use the useful factor that the log of x times y equals the log of x plus the log of y, then we would end up with 20 log 10 of the modulus of h of omega is equal to 20 log 10 of g, and I'm not sure why I'm continuing to write that, because I've already written it out on the next slide. Looks like this. We've now separated all those multiplications into additions and subtractions. And we can see that the effect on the frequency response can be considered to be the sum of all of these terms. An effect due to the parameter g, an effect due to all the zeros at 0 Hz, and then an effect due to each of the zeros and each of the poles in turn. And if we can work out what the effect of one zero and the effect of one pole are going to be, then all we have to do is add up these effects, and we will end up with the amplitude response. And that's exactly what we're going to be doing in the next videos. So a quick summary of this one. We've expressed this frequency response in terms of this standard form, where g times j omega to the power of n is the gain at very low frequencies, where a low frequency is defined as being a long way below the modulus of any of the zeros or any of these poles, any of the roots of the numerator and the denominator, in other words. N, that term there, is just the number of zeros at 0 Hz, or if you like, the number of factors of j omega that you can extract from the original numerator polynomial. Zn and Pn are all the zeros and the poles. Zeros are just the roots of the numerator, and the poles are the roots of the denominator. And in each case, any term of the form 1 plus j omega over minus p naught, like that, if omega is much, much less than the modulus of p naught, then this term here is going to be insignificant compared to 1, and we can neglect it. But if omega is of a similar magnitude to p naught or greater than p naught, then this term here is going to be equal to or much bigger than 1. We absolutely can't ignore it. And in fact, at very high frequencies, when omega is much greater than the modulus of p naught, we can neglect the 1. We'll investigate the consequences of those approximations at both low and high frequencies in the next videos.